So welcome everyone to the day 3 lecture. So today we have Professor Sanjeewa from Sri Lanka, University of Peradeniya, to deliver the lecture. So he will be talking about supercontinent cycle of the Earth. So Professor Sanjeewa is having many years of connections with Japan. So I think it would be better Professor Satish introduce him. So I'm passing on to Satish.
Thank you, Adira, and thank you, Sanjeewa, for accepting our request to give a lecture on this diverse environments. And I was wondering how I can introduce Sanjeewa, because I know him for a long years, and he has been a student. He did his PhD in Japan and has been in Niigata for 1 year, and so we have a long running collaborative work as well. And I have visited Sri Lanka several times, and he has shown his field to us. So we have been working together for a long time, so it is a great pleasure for us to have him today to give a lecture on supercontinental cycle. And in fact, I suppose Sanjeewa is now in Beijing on a visit to China, but although he's now on an official visit to China, he has kindly accepted our request, and I hope everyone will enjoy his lecture, and as well as get good amount of knowledge from his supercontinental cycle of Earth. So Sanjeewa, please.
Okay, Satish, thank you very much for your kind interaction. Okay, let me start my lecture today on the supercontinental cycle. So I think most of the students who are here are familiar with this terminology, because it's so frequently heard now these days. But anyway, I will just, because I know that this forum contains not pure geology students as well, from other fields also. So therefore, I think this will be a very general type of lecture, and I'm not going into much details, but I hope you will all get some extract from this lecture. So we'll see what are these supercontinents. Now present day Earth is like this. We can see our present Earth in a certain configuration. We call the current configuration of the Earth, where we see Africa is southwest of Asia, and Australia is on southeast of Asia. Like that, we have some kind of a fixed configuration, right? So this is what is meant by the supercontinent configuration as well, because it's a kind of a jigsaw puzzle. So we can take pieces of these continents and fit them together so that we will have the correct shape of the globe at a certain stage. Because all these continents are moving, right? All these continents are moving gradually at a very nominal rate, variable among the place to place. We will see some of those aspects as well, why that happens also. Okay. So currently what we have in our Earth is oceans and continents, right? So we have oceans and continents, and we live in different parts, and we are about to see how our Earth was under evolution from its beginning. So, the age of the Earth, how much is the Earth's age? So you can clearly see the numbers here. 4.56 billion years ago, the Earth was formed, right? So that time we call in the geological time scale as Precambrian time or the Hadean time. How do we know this age? That is another question, so which we want to answer. So there are several methods or several materials that we have used for determination of the Earth. For example, lunar samples, the materials coming from the moon, and also meteorites, that is extraterrestrial materials. So these all give us help us to estimate the age of the Earth, and also, of course, the materials of the Earth, very old materials we have found in the Earth as well. So that also gives the age determination. And for this age determination, what we use mainly is zircon, the crystal zircon. It's a mineral, right? It's a very robust mineral. It can resist weathering. That means it does not happen anything under the atmospheric conditions or normal climatic conditions, so that it can preserve its original character for a long period of time. So that is a very useful material that we can use for age determination. So this zircon can host a lot of amount of uranium and thorium in its crystal structure, so that we can use radiogenic isotopes such as uranium-lead, thorium-lead, like isotope systematics. We can use with that isotope systematics, we can determine the age. So any material which is old material, which is very old material, we can use uranium. If it is enriched in zircon, then of course we can find its age by using this zircon crystal. So this is how we have the scientists have found the age of the Earth. For example, in Canada, Augusta province, the Great Slave province in Augusta region, we call Augusta gneiss. That means the gneissic rocks. That gneiss means metamorphic rock. There are three types of rocks: igneous rocks, sedimentary rocks, and metamorphic rocks. And one type of metamorphic rock is gneiss rock. You can see this very nice kind of foliation. So this is what we call, the layering. This is what we call the gneissic foliation. Gneiss, gneiss foliation. It is nice also, right? And also, the Jack Hills. You already heard of this some time ago. There was a paper published in Nature giving the oldest material found so far known in the Earth from a zircon crystal found in Jack Hill, that is in this region of the Australian continent. And this zircon gave an age of 4.4 billion years. So this is the zircon grain found in Augusta gneiss, which has given 4.03. So before this Jack Hill zircon, this was the oldest rock known in the Earth. So like this, people do age dating so that we can understand the age of the Earth. So if we consider about the early Earth, so how this Earth was formed, some kind of dust particles, dust materials, which we call planetary disk, accreted. The material that these the accretion materials, that means the materials that are coming towards each other and forming a more bigger spheres, more bigger materials. So these are called planetesimals, and accumulation of these planetesimals caused little by little to form these planetary materials. So for example, these little bigger ones were made of very tiny planetesimals by accumulating together in a gravitational field, because when this mass increases, the gravitational field also increases, and we call these early materials formed as proto-planets because they are not really planets. They are the parents, like parental materials of the current planets. So therefore, those are called proto-planets. And this process we call Earth's accretion. So this Earth's accretion has taken place about certain period of time after the Earth started initially formed. So it's a long kind of a period, and the end of this bombardment of these planetary materials, protoplanetary materials, has been continued until 3,800 million years timeline. That means 3.8 billion years time. So you can understand the time frame from 4.6 billion years, that is the initiation of the Earth's formation, and then it has moved to this very long period of time. So this is how the Earth was formed initially, and also there was a gradual accumulation of heat as well. The main reason for this is the Earth's mass, when it gets accumulated in the gravitational field, a lot of heat dissipation is taking place. So that's the reason for that. And in the Precambrian or the Hadean times, after accretion completed, these materials were also spinning. So they were also spinning, that means rotating. And because of this rotation, there was a chemical or physico-chemical process happen that we call the differentiation of these primordial materials. That means the more heavier ones, like iron and nickel, they migrated to the center of this rotating body, rotating this early Earth body. And the other materials, which are more or less silica-rich, like silicate material we call, they move towards outer side because they are less dense. Their density is less. So therefore, they came towards the outer side, whereas the more heavy nickel and iron, they sank down into the central region, where we call the core region. So that's how core and mantle was separated at the early stages of the Earth's evolution. So there are only two layers were formed at that time, core and mantle. So then after some time, because of increasing heat, we call the accretionary heat, the heat formed at the time of the formation of the Earth. Because of these, the old materials were under molten stage. So everything was like a sea, like an ocean. We call it a magma ocean or magma sea. And gradually, when heating, the early formed materials will start to cool also, right? While forming the other melted materials. So this gradual cooling has caused these melt materials, that is magma actually, very hot magma, to gradually cool and form more silica-rich or more silicate-rich fraction. That is now what we call the crust. So this is how the crust was formed, and this process we call the crustal differentiation from the early mantle. So early mafic magmas means iron magnesium rich magma, very, very dark colored magma, heavy magma, which was available at the young, very hot Earth at that time, and which differentiated some crustal materials, which are low density, and they were floating in this magma ocean because of this low density. After differentiation, still the early Earth was a magma ocean, and on that, these crustal fragments were floating, and they were more or less like volcanic islands. And since they were dense, less dense, they were floating on top of this magma ocean. And this process continued, and for a long period of time, and different differences also happened during this evolution. But anyway, at the early Earth, at the earliest times, there were no continents, no oceans. But later on, gradually, these small tiny pods of felsic or low density materials gathered and started to form small types of continents, and that continued a long period of time. And even today, what we see is a lot of magma is coming from the mantle, and a lot of crustal materials are dumping on ocean floors or in the continental crust or wherever. So this process is continuing. Earth's dynamics is continuing, but at different scales and different levels. So spatio-temporal changes are there with respect to time and space. Changes are there, but still these Earth's dynamics are going on. So present-day Earth, what we see is continents and oceans. So this is how the early Earth was differentiated and evolved to what we see today. But still underneath this kind of a factory, it is operating. So at the earliest stages, as I mentioned, these are the small islands which were formed due to magma differentiation, and gradually some oceans were also started to form, and it looked like almost what you see around Iceland today, right? In the map, if you see, just isolate the Iceland only. If you see all together, you never see like that. But you can see some similar feature like volcanic island like. There a lot of magmatism is taking place, a lot of volcanoes are there, right? Even in the Iceland, you know, in the middle of the country, there is a volcanic line, right? That's a volcanic line. We call it a rift line. So we will learn about what is rifting later on. The country is splitting away from each other. I mean, it will be split into two fractions in the near future, making a new ocean there. So this continues. So anyway, this is how the early Earth looked like, with small portions of protocontinents adding one by one by this felsic volcanism mainly throughout the ocean system. Also for creating new ocean while cooling this hot magma ocean. And the convection, you know, the heat transfer, right? From the hot mantle, the heat transfer is we call convection. And it was very fast due to high temperatures there that we call the ultramafic magma. That means a very high magnesium content, highly iron and magnesium rich magma, which was ultramafic magma, and of very high temperature. That is why we call it hot magma. And there partial melting of these materials were taking place. Partial melting means it's not the complete melting. It melts partially. Melting partially means you see melt portion and also you see the residual solid portion as a result of this process. This happened as well as while this magma is cooling, crystallization of magma is also taking, fractional crystallization of magma is also taking. Fractional crystallization is also, it's not the complete crystallization, it's partial crystallization. One part crystallizes, that means makes some solid materials, while the rest of the liquid remains, but the composition is different than the previous stage. So this is what the fractional crystallization, which makes both mafic and felsic. Felsic means silica rich, mafic means magnesium rich compositions. And of course, because of this chemical contrast, they will have different densities. So this happens, this had happened during the early Earth and continued with the time. And then what happened at that time, gradually, remember, there was nothing called plate tectonics at that time, right? I will come to the definition of plate tectonics later on, the introduction of plate tectonics later on. But for the time being, those who are aware of this phenomena, just to keep in mind that there was no this movement of dynamic like today. At that time, it was very, very sluggish type of dynamics were there in the Earth's interior, because actually there were no such plates at that time, during that old time. Only this type of pods of continents available within the hot magma ocean, and also gradually formed small oceans were there in the early Earth. So anyway, later on, this because of this convection, and because hot magma means convection always happens. Convection means material transfer also. It's not just the heat going on, it can transfer the material also. That is how you can witness in a kettle, in a boiling kettle. You can put some ink drop there, you will see some migration paths of these ink tiny particles, right? That means it's not just only heat transfers, it transfers materials as well. So this is the beginning of this movement of crustal materials on top of the molten mantle at the early stages. So they gradually moved and they met each other together and accreted on to more larger crustal masses. Okay, so small islands, they move towards each other, or even sometimes it might be away from each other, but wherever they meet, they accumulate and make more bigger landmass. So likewise, this development of landmass were continued, and those land masses we call the proto-continents. Actually, those are not the real continents like what we see today, but because of those early differentiated material, we call them proto-continents, like proto-planets, like, right, early materials. So the present Earth, as I mentioned before, we have well-defined continents and well-defined oceans, but at that time it was not like that. So anyway, this process continued, and later on what happened was, because of these processes, Earth was divided, separated into several density-driven layers, or also chemically separated layers, right? The core, mantle, and crust. So initially I mentioned that what we had was the mantle and the core only, but later on gradually the crust started to appear. But now the present day, we can see even the core is also divided into two, as inner core and outer core. Inner core is very solid, having a lot of iron and nickel solid materials, while outer core is like a liquid type, still nickel and iron. And then mantle, of course, mantle is also differentiated. I mean, differentiation means this chemical contrast. Just keep in mind like that, chemical contrast. So it is also differentiated. That means this upper portion of the mantle. That's why you can see some little color difference here in the mantle layer here. The upper part here, like 100 kilometers or so, that is what we call the upper mantle region. The other part is the lower mantle region. So lower mantle and upper mantle also has some chemical contrast, which I'm not going to discuss today, but just keep in mind those two are also different. So the lower mantle, this lower part is more or less similar to the primordial type of mantle. That means the primitive type of mantle, early mantle, differentiated, early types of early stages of mantle, which is almost undifferentiated. Like, I mean, it's not changed its composition. Like, so we still believe, based on many evidence, of course, that this lower part of the mantle is undifferentiated, more or less. So that means it's like primitive type of mantle. So that's why we call it this part as the primitive mantle, whereas the upper part of the mantle we call depleted mantle or it's chemically changed mantle. Okay, so there are such contrast as well. But anyway, just keep in mind that this Earth's changing into different layers happened gradually with time, like inner core, outer core, mantle, and crust. Very generalized type of 4 main layers appearing in the crust, appearing in the Earth. And later on, this crust was formed very robustly. I mean, a huge amount of crustal differentiation from the mantle happened around, after 3 billion years time. Then this crust was also fragmented like this. So there are so many crustal fragments you can find on the Earth, because this crust, although we see it like a layer, it's not a continuous layer. So it's a fragmented layer. So therefore, there is possibility for these crustal fragments to move relative to each other. That means they are not moving together, all together, but individually they can move. So some can move towards each other, some can move away from each other, whereas some fragments can move parallel to these boundaries. Okay, so these boundaries we call the plate boundaries now, and these plates mark the very, very dynamic regions of the Earth. So a lot of earthquakes, a lot of volcanoes are occurring along these plate margins, because this is fragmented. Of course, you know, once you have a fracture, there is possibility for leaking of liquid materials. So in the mantle, the liquid materials, once heated and transported upward because of heat convection, these materials can come up to the surface. So that's how you see volcanoes as well as undersea volcanoes happening throughout. So this crustal fragmentation caused a lot of movements to the Earth, and that's how the plate tectonics started. So these are the plates, and when they are moving in different directions and different velocities, we call that process as a whole plate tectonics. So this movement of these plates was first noticed or first discussed by Alfred Wegener. He later on found with this concept that all these continents that we see today can be fit together like a jigsaw puzzle. So he a lot of evidence helped him to correlate these crustal plates or continents from one to another, considering a lot of evidence. For example, mountain belts, distribution of mountain belts in the world, and also the species changes, diversity of species, fauna and flora, and also the glacial distribution. Even though now we don't see glaciers in some places, we see the evidence of existence of glaciers. For example, abrasion, some erosion features, like a lot of evidence are there to say that we were in the glacial region some time ago, right? Even in tropical countries like us, like Sri Lanka, India, or Brazil, or these countries, they have a lot of glaciation evidence. So we will see why we see those glaciation evidence later with this lecture. And you can see some similar type of plants, and we call fossils, right? These are records found in rocks now, fossil evidence. That means you can see the imprints of plants and animals recorded in rocks. Those we call the fossils. So this fossil evidence can be found, for example, in South America. If you find some sort of fossil, and that can be found in South African region as well. So that implies at a certain period of time, this South America and South Africa could have been together like that, right? And also other evidence, for example, mountains, right? The distribution of mountains from continent to another, right? Also gives evidence for us to fit them together, right? This is how Wegener started to fit continents each other. So this is very interesting and very important finding at that time in 1912, I think. Wegener configured this continental drift or the floating of continents, the concept. Okay, and also he considered the shapes of continents. Of course, once you see the shapes, you should understand that they can fit each other. So it's not just shape fitting, we have the material fitting as well, like fossils and rocks. So therefore, this configuration or this fitting of continents is realistic and on evidence based. So therefore, it's scientific. So this was a very important finding happened at that time. And this helped people to think that were these continents together some time ago, right? So that's how people started hunting on rocks and other biological evidence as well to more elaborate about this continental drift concept. And then its evolution came as supercontinent concepts. Right. So as I mentioned before, a lot of earthquakes, volcanoes, and mountain ridges mainly mark the locations of plate boundaries. And this is in a world map. If you see, you will see like that in a present day map. So you can see these plates, these tectonic plates. We call them tectonic plates. Okay, these tectonic plates, they are showing their margins with volcanoes or earthquakes. If you map earthquakes and volcanoes occurrences, definitely they will lie along these lines. So that's why this actual evidence has shown us this clear evidence of existence of these plate boundaries. So you can see here the North India, the Mount Everest, and this Tibet plateau. This is also a plate region, continental plate region, and this Pacific Ocean, you can see that it is the Pacific plate. Everywhere it's a circle like, right? So this is full of volcanoes and full of earthquakes. The Japan Islands, so here it's full of earthquakes, full of volcanoes. So this specific ring people used to call ring of fire. Why is that? Compared to other plates or other plate margins, this is a kind of a circular type of a plate margin where a lot of volcanoes are occurring. So it's exactly a ring of fire. So that's why people call it a ring of fire. So anyway, this is how the Earth's crust is there. And so let's see now what causes this floating of these continents, or in other words, we call the continental drift. So you have continents here, and I'm showing the present day configuration here, and another continent here, and ocean here. And you can see the mantle. This is the mantle part, Earth's mantle part. And as I mentioned, the mantle is convecting heat, and it's always moving upward and going down like this. It's a circular path here, anti-clockwise, and maybe here clockwise direction, like that. So everything is coming up and going down. So this exerts some extremely strong forces beneath these oceanic parts, right? So I think I did not mention that this Earth's crust can be divided into two. One is continental crust and the other one is oceanic crust. So we have two parts of crust, continental crust and oceanic crust. And oceanic crust is having heavy rocks. That means iron and magnesium rich rocks. That is high dense rock. Whereas the continents are a lot of silicate and silica and aluminum rich. So therefore they are low density. So compared to these two densities, you should remember that the oceanic crust is the densest one. So once you have this force exerted on the oceanic plate, it tries to move, but because of its heaviness or high density, it moves downwards beneath the continent, right? So under the continent, always oceanic crust is moving down, and this happens continuously so that it can move away from each other, right? So this is one situation where these the plates or the continents drift. Because of this pushing, all these continents are also moving, right? So that's why this continental drift is happening there. And some situations where purely some region like here, for example, the continent region, no ocean is involved, right? So there, still the mantle is there beneath it. So mantle is hot, this mantle convection is continuing. So these forces are still, I mean, the materials are coming up that we call upwelling, and going down material is called downwelling. So this upwelling and downwelling is continuing. With time, after some maybe millions of years, some tens of millions of years, this crustal fragment here becomes sort of thermally weak, okay, because of thermal maturation of this crustal fragment. It becomes weak so that it can no longer bear this pressure here. So then what happens is it starts to split, it starts to fracture from here. So then we call a continental rift zone is generated there. So there will be no more continent there. I mean, a margin will be a kind of a fractured region, and gradually this fractured region will evolve into this type of an ocean later on. Okay, so this was earlier entirely continent like here, but now gradually it's becoming an ocean, right? So this also happens. So this is rifting zones we call, right? This is we call subduction zones, and also spreading zones we call, spreading centers, right? So there are so many terminologies, but just to keep in mind that there are multiple terms that we use for the same situation. We call these tectonic settings. This type of areas we call tectonic setting. Okay, it's a geological term. Okay, so we can see this rifting happening today. If you go to East Africa, right? If you go to East Africa, in the Afar region, in east of Ethiopia and east of Kenya, you will see there is hot magmatism is taking place on the continental plate, right? Very shallow regions, you can see the magma chamber. It's very, very shallow. So that means this part will be separated very soon. In few millions of years time, these two parts will be separated.
Sanjeewa, I'm sorry to disturb you. There are some students saying that your slides are not moving, or I don't know whether is it.
Really?
I also find something because in the same slide is being shown. Can you just stop sharing and then once again?
Can you see now?
Yes, I suppose we have seen on slide number 15, I think, something like
what about this one? Did you see this one, this continental drift?
I haven't seen it, but I don't know about the students there. I think that it was stuck for me also for a while.
Okay, I was around here. You can see now the rifting slide?
Yes, yes,
okay.
It's visible.
Okay.
Please go ahead.
Okay, so because of this mantle convection, this happens, and very soon in the East Africa, you will see the similar rifting is, of course, it's already started. It will separate into two continents, continental fragments, right? So what is happening here is the new ocean formation. And you can see the Red Sea here. And Red Sea means there is an already formed ocean, already formed sea. That means it's a forming ocean. becoming an ocean because of this rifting. So it's a little bit older than this rift zone. Okay, so these dynamics are taking place throughout the time, and you can see new ocean formation in this type of tectonic setting. New ocean forming is visible, as well as in subduction zone. If you go to a subduction zone where the oceanic plate goes down, what happens is this whatever the materials or the continental parts dragging with this being dragged with this ocean plate will be coming. So this drifting of this continent will come closer and closer with time, and they fix they collide and more fix together. We call it a suture zone, formation of a suture, right? Because of the subduction, ending of the subduction will be the forming of a more bigger continental land mass, right? So here what has happened? Disappearing of oceans. So already existed ocean like this will be disappearing, and we call it closure of ocean as well. So opening of oceans that we saw before in rifting zones, and closure of oceans happening in subduction zones is continuing in a cyclic manner, because once subduction is taking place somewhere, somewhere will be rifting as well. Another place rifting will be there. So for example, here the Indian subcontinent was somewhere away about 71 million years ago from today, and gradually it came moving northward, and presently it has already collided with the Eurasian continent here, and that's why we see the Mount Everest and also this Tibetan plateau, and that has exactly shown here as a suture zone, right? So you can see the suture marked here. So this is a continental, we call amalgamation zone also, right? These two continents now have been amalgamated because of this movement of continents. So this happens in cyclic manner, and this is the main cause for continental drifting, right? And this opening of oceans and closing of oceans, in geology we call, because it's cyclic, we call it Wilson cycle. Actually, it's related with Earth's dynamics, and because of tectonic forces, that means the forces that are acting beneath the Earth, we call tectonic forces, and due to that, you can consider it as tectonic episodicity as well, because and at one place you have subduction, and that subducted materials will be going down and melted and come back again in a rifting zone, right? So likewise, it happens in a cyclic manner, and this figure clearly explains about this the same fact that I have been showing you with diagrams before. This explains the Wilson cycle. So this Wilson cycle is very important for supercontinent concept. So that's why we consider the Earth was once in a different configuration than this today, but again in the future this will be different, right? So this is what we call the tectonic episodicity. Okay, for the tectonic episodicity, the first what you need is rifting, splitting of the continents, and then the oceanic crust moving, and you can see subduction here, so that is required, and then cooling is necessary because of this subduction, and then at the margins of continents, what happened is there is no magma here, so it's relatively cool, and also because of the erosion and all, some sediments are coming down from continents to the ocean, and they get deposited, and they accumulated. So this happens. So we call this part as a passive margin, and this part as an active margin, because the volcanism and many magmatic activities are taking place. And then what will happen? At a certain period of time, this subduction will finish by collision of the continent, and beneath the continent it's moving down, and a lot of volcanoes are also coming up because of friction. There are a lot of frictional forces applying here that cause additional heat, and that heat cause the subducting slab to be melted, and that melt is coming as volcanoes as well, right? So this continues, and finally what happens is the terrains accretion, then they weld each other together to make more material added to the existing continent. So it becomes a more larger continent. That means this continent will be growing more and more, and finally this oceanic part will be disappearing because of this convergence. We call this convergence because they are coming together towards each other, and that is also called the terrain accretion. So this is also a requirement for tectonic episodicity. And finally, this is the result of accretion of these terrains, and you can see some continental parts and new continental materials, the new sediments that were there, and also the previously existed oceanic materials, right? Because you had the ocean here, so these oceanic materials will be incorporated here. So that's how oceanic materials are now appearing in our continental regions. Okay, so this causes that kind of accretion. So it will definitely build a chain of mountains. So this is a mountain building process which we call an orogeny. Okay, in geology we call orogeny. Orogeny means mountain building process. So it means the creation of mountains. It extends some thousands of kilometers in sometimes. You can see the Andean mountains or the Everest mountain range. Very long mountain ranges can be formed because of this tectonic episodicity. And this process will continue because, you know, this once you have these mountains with the weathering conditions and climatic conditions, what happens is erosion and defragmentation of materials happening, and they go down to the lower elevated areas and deposit in ocean places again, and sometime later again because of mantle forces, this continent will rifted, will fractured, and again the subduction will start. So like that, rifting, accretion, orogeny, these three processes will be happening in a cyclic manner. So this is what we call the tectonic episodicity, and it continues from long time ago to the present day situation. So this is the actual reason for us to have cratons as well as supercontinents in our Earth. So cratons, as you just hear, I will explain it later, but just keep that is also a continent, a large continent, right? So all these are all together now we see as very huge land masses in different configurations of the Earth. Okay, right. So this process continues, as I said, and the cratons means very stable old land masses which we see today. Okay, very old land masses which are stable. Stable means they are not moving any longer, probably for a given period of time, but that period of time, of course, with respect to our lifetimes, is very, very long. So therefore we call it, they are very stable for a long period of time, and being they are very old, they are because young materials are always there in active regions, in the subduction zones and rifting zones, like the young materials are there. But these stable old materials are accreted as cratons, because, you know, at the very beginning of the time, early Archean, I mentioned it before, there were no large land masses, only some pods of volcanic felsic materials dumped in those regions, but later on they accreted to form little bigger not little, bigger masses. So they formed Archean cratons. We call those Archean means that time. We refer it to the old age. So these were results of accumulation of these continental materials. So if you see the timeline here, this is 4.5 billion years ago at the time of Earth's composition. This is the upper continental crustal composition I am showing you here, line with respect to the age. And you see at very old ages time, like 4.5, 3, there was no continental crust, of course, right, during that time. So you don't see any crustal material there. But later on, I said differentiation took place, started, and material started to form as the continental crust, and then they gradually become dumping more felsic material because of magma differentiation. Okay, so this is a critical time, around 3 billion years. Sometimes it's like it's not clearly clear-cut marked, in still under debate, this 3 or 2.5 time as the starting time of global plate tectonics. Until that time, there was no plate tectonics. So that's why these early cratons, they are just lying there as isolated without moving dynamically. But later on, the global plate tectonics started with, of course, you know, to start the plate tectonics, you must have the crust formed, right? So that's why it takes some time to start the global plate tectonics. So you must have a density difference, right? Unless you have a density difference, there will be no dynamic flow. So that's the reason, actually. So anyway, this is a kind of a transition time from early dynamics to global modern type plate tectonics. Okay. Is it clear up to now? I mean, you are seeing all these slides clearly up to now? I
Yes,
need
yes,
some
sir.
feedback.
Yes, sir.
Okay, great. Thank you. Right. Okay, early continents. Again, for some examples I can give you, like in Australia, you have the Pilbara shield. Sometimes these cratons are also called shield areas, okay? Precambrian shield areas. And Canada, South Africa, there are so many regions where these large cratons are there. And they are full of green color materials as well as light color, whitish color materials. So you can see this in the field, actually. It's a kind of granitic gneisses, but it's like we call TTG, tronjomite gneisses, TTG, and also some chlorite-rich metamorphic rocks we can find. We call them greenstones. It's a chlorite because it's a greenish mineral, so it's rich in clay-rich materials were there. So they make these terrains very distinguishable from others. So we call them greenstone belts. They are very old in these regions. Specifically, you can find in other places in the world also, you can see. And they are now accumulated with other continental fragments. So we can see because of these tectonic dynamics of the Earth that I just mentioned you. And this is an example of greenstone belts. And you can see some regions are felsic, I mean light colored, and some regions are greenish appearance is there, right? So these are greenstone belts. And also this distribution of these Archean rocks, these very old rocks in different places of the world. But you don't see they are distributed everywhere because because of this plate tectonic motions. I mean, their dynamics are so vigorous. So many materials are now either melted or disappeared during these processes. And if you consider all these continental accumulations, and most of the Earth, when all these continental and oceanic or whatever these regions, especially the continental fragments, accreted together, when they amalgamated together, more than 75% of land mass, then we call it's a supercontinent. Okay, so from the whole Earth, if it is more than 75%, if you see any continent, then you can call it a supercontinent. So that is the general definition of supercontinent. But now there are some deviations also. But anyway, this is how the supercontinents were defined, and their description was initiated at that recent literature. And cratons and proto-continents, the early continents and also these cratons were later evolved into supercontinents. Okay, so this is a very interesting dynamic happening in the Earth, and a lot of geological features are used to correlate them, right? A lot of geological features we can use to correlate them, and we'll see some of them, a few correlations we can see later on. And let's see the key events happened in this geological time scale. You can see at the very earliest time, what you saw was, for example, the formation of the Earth, and then we saw appearing zircons, old zircons in Australian rocks and Akastan ice, the Canadian rocks, right? So all of them represent very earliest ages of the Earth, right? Very earliest part of the Earth. And later on, more younger crustal materials were found, and greenstone belts, associated felsic terrains like, and they all represent the very earliest history of the Earth. We call all together as protocontinents for them, microcontinents plus the Earth's earliest cratons. And then we all these early continents were there in different configurations, and these cratons and protocontinents actually people used to call super cratons, because they were also accumulated into bigger land masses, but not as large as the supercontinents. But still, some people used to call it supercontinent or old supercontinent or supercratons. But anyway, these cratons or protocontinents were there in different configurations. So the oldest configurations, or the assembly, that means the configuration, how they fit together. There were three such: Arctica and Atlantica, right? So these three. But in some literature, you might see these three together called superior supercraton, right? Sometimes it's called superior supercraton, but you might see in some literature these three names. Okay, so this is the oldest assembly. It happened from 3000 MA and then continued up to 2000 MA. This early supercraton assembly continued in the early history. And then you can just see there little bit details, and also you can see some kind of descriptions, because you know, the present day continental regions were also represented by at that time, because now, you know, all the today's what you see today is also part of Archean or Precambrian evidence, right? You see here in the map, the Archean materials are there, right? So these are helpful in our continental configuration. So you can see these materials distributed in those early supercratons, in these three supercratons in different manner. Okay, this is at least about 2.5 billion years time. we are talking about the configuration. And and then we have more and more bigger land masses forming. For example, when it like 1800 MA, 1.8 GA to 1.5 GA, another bigger land mass formed because of accretion of these early masses. They combined together at about 1800 MA time, forming a more bigger continent. That is again bigger than 75% of the Earth's landmass. Therefore, it was called the first supercontinent in the world, in our planet. That's called the Columbia supercontinent. Sometimes it's called Nuna supercontinent as well, right? Nuna or Columbia. And then later on, after this supercontinent, again some changes happened to this supercontinent. I will explain as why these changes happen later on. And at about 1100 MA, that means 1.1 GA time, another supercontinent formed. That means the Columbia broken down into pieces, and those pieces will combined together, forming a different shape. So that shaped continent was also a very big one. That was called Rodinia. And then after that, around 500 MA time, the Gondwana formed, right? Another supercontinent, which was attached with another part of a bigger continent called Laurentia. These two, but usually we call Gondwana as a single continent, supercontinent. But there are some new definitions or new deviations for this supercontinental definition also. I will give you that at the end of this lecture. And finally, the latest supercontinent formed was the Pangaea supercontinent. That was about 250 million years ago from present. So anyway, this dispersal or drifting caused these existing supercontinents to fragment, and they were floating because of this mantle dynamics. And then finally they get together and form into a new configuration, right? So dispersal and amalgamation is a feature of very characteristic feature and very necessary feature for supercontinental formation. And this is the timeline for these supercontinents. You can see the earliest ones, and then Columbia, Rodinia, and Pangaea, right? So early ones we call the protocontinents or protocratons, and then these after 2005 billion years time, whatever we have encountered are called supercontinents. So it's almost the timing of the modern plate tectonics is like nearly 2005 billion years time, right? So that's why these dynamics were kind of agitated like at this time, whereas in these Archean times, it was more sluggish, very boring type of dynamics were there. The Earth was not vigorous. I mean, heat-wise it was vigorous, but not the tectonically, because there were no big continents to float also. Anyway, this tectonic vigorous nature started after 2.5 billion years. So that time frame, we think that the timing of starting the modern plate tectonics. Okay, so as I explained before, through the action of plate tectonics, all these dispersed continents can merge into a new single supercontinent. Okay, so this makes a kind of puzzle, joining pieces of puzzle that we call the reconstructing the supercontinent by using the present day evidence. Okay, so this is very, very important because we have to use a lot of age data as well as the lithological, geochemical, structural, geophysical, seismic, everything. All the details should be combined together, and we have to reconstruct this past environment using the present day evidence. Okay, now let's see why this the supercontinents once formed, why they disperse. Right? Dispersal means they fragment into pieces. This also happens because of mantle-driven dynamics. Right? Once in some hundreds of million years time, from very deep part of the mantle, that is almost the lower mantle, even the core mantle boundary region. Okay, some thousands of kilometers below, very, very hot magma is rising. Even now, today, this moment, there may be such a huge magma flow is rising upwards. Okay, so that magma is not the normal magma like you observe in a volcano in Japan or Indonesia or wherever, in a mid-ocean ridge, wherever you see. That magma is different from this particular magma. This is very hot, and geochemically also they are different. They are more, we call more enriched type of magma that comes up with a huge temperature as well as huge force can be applied, and because of that, this supercontinental lithosphere, supercontinental solid rock layers can be fragmented, can be weakened and fragmented, and it can start to break down into pieces, right? So that happens. We call it plume heat. Plume is the uprising hot magma. Okay, and so this can happen for this dispersal of supercontinents, and then with plate tectonics, again, what happens is these fragmented crustal sections will some are subducting, some are colliding and forming new land masses, and they become sutured to each other and form more and more bigger continents. And if it's making a huge land mass, like more than 75% of mass area, it will become a supercontinent. So this is the continuation of this tectonic episodicity, and the Wilson cycle or the subduction collisions procedures that continues throughout the history from long time ago to the present day Earth, changing the shape of the planets. So here you can see some distribution of old rocks and some young rocks in the crustal distribution, in the basement rocks, that is the rocks that you see on the surface. And you just keep in mind their distribution. So many old rocks you can find on the continents, right? So see, 3.8, 2.5, long time ago formed rocks. Okay, now I will show you another image which shows only the ocean. Okay, this is ocean flow. This ocean flow shows some ages, and this is the key to that. You can see the millions of years here. 0, that means today, present day. These are the mid-ocean ridges where the magma is coming today and dumping there. And you can see the ages. For example, this blue color, it's like 130 million years, 150 million years, 180 million years, like the range. Okay, you can see that is there somewhere here in the Pacific Ocean, and some part here in the Atlantic Ocean. But it is very little area wise, but you can see the present day area distribution is large, but older ones very little. But you don't see any age older than, say, 200 million years. This is 180, but it can go up to 200. So that means in the ocean floor, you never see a rock which is older than 200 million years. But in contrast, you saw on the continents, there are so many rocks very old, 3.8, 2.5 GA, like that. So why this is happening so? This is the, again, plate tectonics, right? You know, this oceanic crust is subducting beneath the continent, and whenever it is formed along this mid-ocean ridge, this is the place where the oceanic crust start to appear. That is why it's 0 million years, today's time. And with time it moves because of spreading, divergence, it is moving like that, and somewhere it meets a continent, and then by that time it has like elapsed 200 million years, and beneath the continent, because of its high density, it subducts. So it disappears. So in the ocean floor, you never find older rocks than like age older than 200 million years. So this is how the age distribution you can find in oceans and also continents, and that contrast reflects our tectonic cycle. So we have already discussed Colombia, Rodinia, Gondwana, and Pangaea, these continents. And if you see the Colombia supercontinent, this is the Colombia supercontinent. So once it formed at 1800 GA, right? It was like this, and you can see a lot of continental fragments, areas like North America, Baltica, Siberia, North China, Amazonia, India, Antarctica, Australia. So many areas were included in that, and they were also facing the similar subduction collision tectonic regime. So this is the this was like multiple places. At multiple places you can see the subduction collision. For example, here you have the North China here, number 5, North China, and it goes down, or it subducts beneath number 4, that is Siberia, here, this place. So this is given in this cartoon. So similar type of tectonic settings are there in elsewhere also in this Colombia supercontinent. So we had multiple subduction, accretion, orogeny events, so that this was this evidence was there for this supercontinental cycle for forming as well as the dispersal. So this graph shows the areas of the collision and subduction, right? With the dated ages with the zircons, right? So they also represent different time intervals, so that here you can see a lot of formation ages close to 2000 MA. 2000 MA here, that represents the Colombia supercontinent formation. So likewise, there are so many evidence, and later on what happened for the Colombia was it was started to rift because of a plume heat. That's how we believe. So this is what we call the rifting of Colombia. That is that has happened around 1.5 GE time, and that rifting along the North America and Laurentia, right? So this part here, you can see the legend here. When you get the video of this lecture, you can slowly go through that, okay, to understand these multiple orogenies. It started to rift away, and you can see now the next supercontinent is in the making, right? The next supercontinent was the Rodinia after Colombia. So still the Rodinia was not formed, because you see a lot of spaces are there. I mean, there are so many oceans in between. So only if all these, most of these continental masses were together, like here, you can call it a supercontinent. Otherwise, it's not a supercontinent. So it is still in the process of formation, and you can see this lot of rifting and collision are taking place. So here you can see the collision after rifting. What happens is collision. So this continent was colliding with this part, right? And that was forming a orogenic mountain belt. So this reddish color belt shows orogenic mountain belts. So in the Rodinia formations, such kind of a huge, long mountain belts were pervasive within the globe. So we call the granule age orogenic events for that. So these are some of such evidence. And finally, this assembled the Rodinia supercontinent. And this is the Rodinia configuration at about 900 million years time. By that time, it was completed. But, you know, supercontinental assembly is not just a very quick process. It takes time. Some hundreds of million years it takes, because, you know, the rifting of Columbia started at 1.5 GE, right? But completion of the formation of Rodinia happened at 900 MA, right? So that means from one continent to another, one supercontinent to another supercontinent, at least 800 or 700 million years has taken place, right? In this example, according to this example. And some age data as well as geochemical data also help us to reflect this supercontinental assembly. For example, here, this graph, you can see the strontium isotope evidence. For those who are handling isotopes, I think it will be easy to understand, but others, I suggest you read some literature to get some basic knowledge about the radiogenic isotope geology. Anyway, you can see it's a kind of a wave type change with time, and increasing, decreasing trends are there. So all these increasing, decreasing trends reflect some kind of collision or some kind of subduction. Okay. So for example, growth, if it is related with growth, that means a lot of crustal materials are forming. So then strontium isotopes will be, signature will be given higher values. So if it is depleted means, if it is decreasing means, some mantle materials are coming up. So that is rifting, right? So likewise, you can understand this tectonic episodicity in terms of geochemical data as well. So anyway, you can see this breakup of Rodinia is not very well dated, because it's the time span is very large, right? Here you see it's a huge range. So it has taken about 800 to 700 million years. But anyway, it is well reflected. This large time span is well reflected in this geochemical data as well. And if you again see what happens to Rodinia after formation. So Rodinia formed, and after 200 million years later, 900 is formation time, and after 200 million years later, at 700 million years time, that is here, rifting started, right? Of course, rifting might have started before that, but the significant rifting in Antarctica and North America started at about 700 million years time. Okay, so then it started to drift. After rifting, it starts to drift, right? Rifting means you are forming new ocean here, right? New oceans will be formed, and this rifting happens afterwards. Sorry, my arrow should be opposite, right? It's not this way, it should be the other way, because this is the Rodinia at 800 million years time. But anyway, remember, once rifted, the continents will be drifting, forming new oceans, and some places it will close some oceans because of collisions. So this is cyclic process. As I said before, it continues. And you can see this region, West African and South American blocks, again rifting, because this is multiple rifting. Remember, in Rodinia, multiple rifting, it's not a single place, and they multiple rifting taking place at different time intervals, and different parts will be rifted from each other, and they gradually move, and maybe somewhere else they will meet each other to form the next supercontinent, that is Gondwana, right? So you can see the rifting here along these black lines. This is the Yucca Ocean opening, right? So likewise, different places, new oceans form, and some places existing oceans disappear, right? That has happened during, for example, the Mozambique Ocean. You can see here at the Rhodinian configuration, Mozambique Ocean is here. But once it comes to the Gondwana, Mozambique Ocean is disappeared. Okay, so likewise, these disappearing and appearing oceans happens, as I mentioned before. So finally, the Gondwana formed almost at about 500 to 600 million years time. The main tectonic activity happened was the East Gondwana and West Gondwana suturing or fusion. So you can see here in the Rodinia, this part is the West Gondwana and this blue part is the East Gondwana. Right here, see East Gondwana and West Gondwana. So those two sub-land masses, sub-supercontinents, collided each other to form the huge supercontinent, the Gondwana. Okay, and so likewise, there has been these multiple orogenies in this Gondwana supercontinent. So you can see the Gondwana configuration here: Antarctica, Australia, India, Madagascar, Sri Lanka, Australia, Kalahari Craton, South Africa, Africa, Congo, South America. All these things are now sutured together into one supercontinent. But remember, the Laurentia is still there. Okay, this part is still there, which is not part of the Gondwana. Right? I will come to that later. It's almost like we have forgotten Laurentia at the time of Gondwana formation. Okay, so next, what happens to Gondwana? Gondwana started to rift. Again, the cycle starts. Maybe a plume hit, and they started to fracturing. Then it drifted, and somehow, finally, the Laurentia was also there, and Gondwana was also there. So the fragments of those were floating to combine into another supercontinent called Pangaea. Right? The Pangaea formation was at around 200 million years ago, but the rifting of Gondwana started at about soon after 500 million years time. Right? So we'll see some of rifting associated with Gondwana. So after the breakup of Gondwana, what happened? The Laurentia here, the Laurentia moved to that time equator, right? Not present day equator, right? At 510 million years ago, equator was like this, because this is another lecture about the coordinates, but remember, this is not the present day coordinates. Okay, and then what happens? The Laurentia here, and then Laurentia had some small orogenies and accreting small blocks. Baltica, for example, North America, like fragments, and the existing oceans were closing, and some oceans were newly creating again. And later, around 400 million years, the collision of Laurentia with the Baltica here, this Baltica, North American continent, they collided together, closing this ocean, and they formed a more bigger continent that was named as Laurasia, right? Sometimes called Laurasia. Okay, Laurentia with Baltica, it formed a new continent. And you remember, we had the Gondwana, right? So Gondwana is also here appearing, because they are moving along this globe, right, at different coordinates. And then again, some at about 340 million years time, Laurasia began the collision again with the Variscan orogeny here, and the Gondwana is also here, right, very close to that now. So finally, another orogeny came, Appalachian orogeny. Here, big mountain range formed, and then the end product of Laurasia with Gondwana collision made the supercontinent Pangaea. Okay, so it came as again multiple orogeny events resulting that. So for this, it took about more than 300 million years time. So at 200 million years ago, now we had the Pangea that included all the land masses almost together. Because in the Gondwana, you see, the Laurasia was separated, right? It was not together. But this term Pangea itself means all lands. Probably due to that, I don't know exactly, but I think like that. Okay. So anyway, the Gondwana, the Pangea formed finally after Gondwana rifting. And this periodicity of these supercontinents that we have discussing so far, due to rift phases, there are several phases. Rift phase, that is definitely driven by mantle plume, right? Because you need huge strength and also a lot of very high heat. Otherwise, you can't thermally weak these thick continental fragments, right? These are huge land masses. We see that it is more than 75% of total land mass. So it should be huge. So to fragment it, you need a huge force. So that's why people believe it should be a mantle plume. And then drift phase. Once the mantle plume hits, it starts to drift, and then drifting and forming passive margins or deposition of sediments, subduction, everything is there along with soon after these two phases complete. That means collision, the final suturing happening, subduction, and subduction ends with a collision, and then the suturing happens, and of course soon after suturing there will be rifting again, right, just to maintain the equilibrium, right? So that is different thing. It's not the supercontinent fragmentation, it's just a continental fragmentation, right? It's a local scale. So about this all this history gives us an idea for these all cycles. It takes about 750 million years interval line, right? So this graph you can see about 750 million years interval that is considered as a the frequency of supercontinental cycles. So this is understood by zircon ages because it's very important to understand the zircon ages to see this supercontinental cycle. And a lot of river sand zircons from different continents have been dated by people to see these pulses, these age pulses. You can see the age pulses here. And so this is from Amazon, North American rivers, and also here the African rivers. These pulses are visible, right? Not only there, and in India or Eurasia, in East Asia, everywhere you can see this. These pulses are very prominent at the respective ages where these supercontinents were forming. So that's very interesting feature. And also we have some evidence from different places in India, and you can see here Adira's work as well. That also shows supercontinental peaks, formation edges, right? Hafnium isotopes, they represent different variation. I'm not going to make you very much details on this because here not only the geology students are there, but anyway, this work, the global configuration of these zircon ages have helped us to better understand this supercontinental cycle. And you can see even here another graph. This is also showing ages from zircons as well as hafnium isotopes from a global database. They are also showing increase decrease patterns that indicates mantle input as well as crustal input. And oxygen isotopes also giving us similar type of results with respect to the time, increasing decreasing patterns, right? So that is also representative of mantle input and crustal recycling, okay, subduction. And so this has helped us to understand the supercontinental cycle with time. And here you can see the distribution again, and what happens in the future from today to the next next supercontinental cycle, because Pangea completed. Now the Pangea has drifted, and we are now in a situation like here, because you know at the Gondwana times we were together everywhere. I mean somewhere here in the glacial regions, but now we have drifted towards the present day equator, right? So what happens to the next next million years, some few hundreds of million years time? There will be again mantle plume, right? So two causes can be there, because the continents are the insulators, of course, because they are large land masses. When it's a supercontinent, that is more prominent. There will be heat accumulated, large amount of heat accumulated, and they get thermally weakened, and the mantle upwelling plume material can easily hit and break them. The other cause is there may be a lot of subduction of large volumes of oceanic lithosphere that is much cooler, and they dump material in the interior of the earth, and cooling and hydrated materials are coming inside means you are adding some water into the mantle. So adding water into the mantle means you are decreasing the melting temperature, right? So you can decrease the mantle temperature by adding water, and that escalates melting. So you are decreasing the melting temperature, okay? Solidus temperature changed. So therefore, these two reasons can be very contributory for the next cycle of supercontinents. And there is double-sided subduction along this region, this star place in the Pacific margin here, and you can see two subduction here, whereas the Eurasian plate margin is also here. It is colliding here, and one subduction is happening in this Western Pacific region, and the other subduction is happening along this Indo-Australian plate region. So these two subduction also makes a huge amount of water going into the mantle, and that can cause enhanced mantle melting, and that can easily help for the upcoming mantle plumes to branch out and hit the present day continental. You know, the mantle plume, when it comes to the shallow regions, it branches out, okay, like here, so that it can cover more regions of the continental lithosphere, so that they can break through a lot of continental fragments. So in the future, so today after Pangea we are here. Now we are almost in a phase like called Eurasia. Eurasia, it's not a supercontinent, but because the old landmass is not together, therefore we can't say this configuration as a supercontinent. So this is 0 MA today, present day. But in another 200 million years time, there will be a new supercontinent coming up that is called Amasia. Okay, so Columbia, Rhodnia, Pangaea, Amasia will be the main supercontinents that we see in this cycle. But in this instance, I want to a little bit confuse you, because if this Columbia, Rhodnia, Pangaea, Amasia is there, but you don't see Gondwana there as the supercontinent. See, this is supercontinent: Columbia, Rhodnia, Pangaea, and Amasia. Why not Gondwana? So far we considered Gondwana as a supercontinent, right? But you know, the new research trend is like defining supercontinent term in different way. Okay, if the landmass is not exactly like covering the whole entire Earth, they don't want to call it a supercontinent, right? So I just noted you on the way that Gondwana was there at the same time. There was Laurentia aside, right? So that doesn't mean they were together. Okay, so therefore, people consider Gondwana instead of a supercontinent, they consider it as a mega continent. Okay, this is a new terminology. So anyway, they have redefined some of these continents as well. For example, Nuna we call as a synonym for the Columbia. But now people call Nuna as a mega continent, not a supercontinent, right? So likewise, there has been several. So likewise, today our configuration, Eurasia, this configuration, the present day map we see today is a mega continent, right? That will join with other land masses once they join all together, will form the Amasia supercontinent in the future. Okay, so with this, I think my explanation is ending, but I want to finish it giving you one important fact about this mega continent, and it's according to their definition, the latest paper. Sorry, you can't see the reference there. It's here, Wang et al. 2020. The supercontinent Pangaea was preceded by the formation of Gondwana, a mega continent about half the size of Pangaea. Okay, so that's why they call it a mega continent, right? So it's half the size of Pangaea. The other part is Laurentia, right? And as a supercontinent breakup, a mega continent assembles along the subduction zone girdle that encircled it and at a specific location, because they just assemble together at a specific location, and for the mega continent then migrates along the girdle where it collides with another continent to form the supercontinent. So that is the newest type of definition related to this supercontinental assembly. And I want to give you some homework for the students. You refer these two papers. These are the most recent two papers on supercontinental cycle. Mitchell et al. To 2021 in Nature Reviews Earth and Environment. And also the geology paper, Wang et al. 2020. They describe about this mega continent concept as well. So with that, I would like to end my lecture. Thank you very much for your attention, and I apologize if there was any technical fault. Thank you.
Thank you, Sanjeewa sir, for your wonderful lecture. So, any questions from students?
Yeah, the student number is 079K. I don't know who is he, but please come on and ask. Yeah.
Professor, thank you for your presentation. It's really interesting. My question is, considering the periodicity of the supercontinent, I wanted to know if the Earth still keep its weight, I mean its dimension during this periodicity. Does it lost some weight?
Yes.
Yeah. Does the Earth lose its weight or some element during the periodicity, or it gains the weight?
Well, yeah, I consider it as an important question, but you know, this is a cyclic process, and at subduction zones, of course, we lose the material, and but you know, they go down into the mantle, and they melt, remelt, and come back in a mid-ocean ridge. There is, for a temporary period of time, there could be some imbalance of this material, but of course, as a whole, for the Earth, there will be no weight loss, in my opinion.
Okay.
There shouldn't be a weight loss.
Thank you.
Okay, you're welcome.
So let me once again thank Sanjeewa for a wonderful lecture today, and thank you, Sanjeewa. And I am very glad that students got a lot of information about the past supercontinents and why you call it a supercontinent and not a megacontinent, or and so on, and the future, how we look at the supercontinent cycle. So once again, thank you very much. And I suppose the students may give you a report. Not everyone. We have given them a choice to select from lectures. So some of them will be giving reports on about this. And when the reports are submitted, Adria will check it and then forward it to you. Okay, once again, thank you, Sanjeewa. Thank you for your effort, and thank you.
Welcome. And thank you very much for giving opportunity as well.
Thank you.
I wish all the students good luck.